All right, I think we'll go ahead and get started then. Good afternoon, and thank you all for joining us for this session in our Enabling Canadian Innovation Virtual Conference. All right, without further ado, I will pass things over to Rob, our Director of Metrology Systems, to get us started.
Thank you, Jessica. Good afternoon, everyone from rainy Toronto. Thank you for joining us today. I'd like to quickly introduce the presenters, which will be shared between David Lee and I. David is our lead application engineer for our metrology systems, and I'm on the business development side. So hello and a good afternoon, everyone. There'll be a lot of metrology keywords and terms thrown around in the next 40 minutes, and your key takeaway should be that as part iterations move from rapid prototyping to production, and fresh designs are coming off the overnight additive machines, that CAD Micro Solutions has the measurement expertise to meet your evolving QA requirements. We'd like to jump right in and with three basic poll questions. It should just take us a few seconds to put together, and then we'll move right into the presentation. So the first question here is, have you or your company ever investigated switching to MBD? If you don't know what MBD is, that's what this presentation is about, but it stands for model-based definitions. So either yes, no, or unsure, and then we can quickly go on to the next one. How are you currently doing your FAI? So if you are involved with quality control at your company, and you've measured a part, whether it be by hand or CMM or a gauge or a robot, how are you currently doing your first article inspections? So we're just curious about that to gauge the audience, whether it be a Microsoft Excel form, a report, a stats package, or other. Your input on that would be greatly appreciated. And then we have one more quick question. Do you know SolidWorks MBD and inspection work together? A difficult question because if you don't know what MBD is, you don't know if it can work together. But essentially, yes, no, or not sure, because we're going to show you how they can work together afterwards. All right, so at this point, we're going to get started.
In this presentation titled Structured Framework for Engineering and Inspection, we are going to focus on the new features of SolidWorks MBD and SolidWorks Inspection, including features within the add-in modules and the standalone client modules. We'll also be showing you how these two things can work together. Lastly, we're going to illustrate how these new features can be used with additional tools to create a robust, closed-loop inspection system. Many of the roles required to carry out this closed-loop system include team members from both engineering and inspection departments. We'll also highlight how some of the tools touch other software packages where the user can exit or continue on with the loop. Let's get started. SolidWorks MBD is model-based definition. It's also associated with PMI, product manufacturing information. Together, they are an initiative to augment or replace 2D engineering drawings as design documentation. What that means is we've traditionally looked at parts with 2D prints. Obviously, the more complicated part, the more complicated print. And we're transitioning from this sort of documentation into MBD, which is tagging all of the 3D attributes on the part with their related dimensions, GD&T, or notations. SolidWorks 2021 model-based definition has two big upgrades. One called MBD datum targets, and the other sheet metal bend reports. Now, in the part we're going to be carrying throughout our presentation, this plastic injection molded part that the additive manufacturing group used in their presentation, and we'll be sharing this afternoon as well. It obviously doesn't have any bend reports, and if you'd like any information on that, you'll be able to find it on the web later. So we're going to focus on the MBD datum targets and show you one of the really nice, cool new features in 2021. So let's switch over to SolidWorks 2021. And here you can see the same part with several pieces of MBD already tagged on it. And to show the new datum target feature, I'm going to zoom in on datum C here, which you can see is this small plane. and I'm just going to go to my MBD tab and select datum targets. Now what's interesting is, why would you use a datum target? These are often used if you want to define inspection points or assembly points or anything like that. And what you're able to do is you can identify obviously regions on the model where you want to pick. You simply assign where you want to put the label. You can do some more advanced things, such as assigning a target radius that the uh, target has to lie within, and then just a location for the flag. What's interesting to note here is that you can also use your standard SolidWorks toolkit and actually assign parametric dimensions to these datum target locations. So if I wanted to control where that target was relative to another feature, I use my standard dimensioning tools to assign where it needs to be. So I'll just do that for for each one, and again do that for the other one over here. So what it allows you to do is, again, if you've got applications where you want to assign datum targets to MBD dimensions or to your model via MBD, there's now a mechanism to do so. While we're in this MBD world, I'd like to share with you another tip and trick that was recently shared to me by one of our partners, and that's the ability to balloon labels right inside of the MBD itself. So if you look at this kind of call out here, one of the things we'll be talking about is the ability for SolidWorks Inspection to do this. But if I simply click on the dimension and look at the tree control, I can come down in here and actually use some new notation that was shown to me, where we can uh, explain what I'm typing here, where I can put some things in brackets. Whatever's in brackets going to appear on the label. I want the symbol to show a circle. I'm going to be identifying it as a number, and I'm going to start at the number 1. And very similar to what you may see in SolidWorks Inspection and the ballooning, we can also put these tags on the MBD dimensions as well. Now we have to do it one at a time, but it's still a valid way to do it. And you can see there that I've now put the number 1 sign on that concentricity. A really nice new little tip and trick feature. So if I wanted to do that again, I could just come down here and kind of add the necessary file structure to do that. See, I want to, in a circle, I want a number, and this time I'll call it number 2. So that's another neat way to uniquely identify different characteristics or dimensions that you want to control in the MBD level. And again, whenever you're doing projects like this, because they're all SolidWorks objects, one of the really nice things that we can do out of this is, if I just capture this view as an example, I'll just say capture 3D view and hit OK. What I would like to just share here regarding the MBD and the new features is you can also post this out to eDrawings. So if I go out to just to produce a generic eDrawings report out of this, you'll notice on the back end when it appears, I've got the new datum target symbols and some other special new features about how to interact with the MBD inside of an eDrawings. So a nice way, you can obviously recall specific views that you had in the drawing before. If you highlight dimensions with the balloon, it shows you on the model which ones. So a great way for you to share between OEM and supplier dimensions that you want to control and how to communicate that information without having to do it the traditional route of Excel sheets or things like that. So I just wanted to share those 2 additional things with you. So again, the major new upgrade inside of our update in SolidWorks 2021 for MBD is the assigning of datum targets and being able to dimensionally control them with standard SolidWorks tools. So without further ado, we're going to move on to what is SolidWorks Inspection. And I'm just going to jump back into my PowerPoint presentation. And what is SolidWorks Inspection? So you've heard me mention that we can already assign balloons to things and control elements to objects. What is SolidWorks Inspection? And SolidWorks Inspection is used to create documentation to communicate dimensional or inspection requirements. at a high level, it balloons your drawing. So ballooning at the MBD level was one way to do it. Doing it with these red targets now is another way. It is a separate software module, but it has a lot more value-added features than just putting those balloons on there. You can do it with SolidWorks drawings or actually drawings, PDF files from external to the SolidWorks community as well. So if you've just got a PDF file, you can use SolidWorks to do this as well. Traditionally, what this looks like is you can bring in a PDF file. Here's the same one that I had on a slide before, and go through the process of assigning a number to these drawings. And the reason that we would do that is we would then give these marked up drawings to inspection, for example, or give it to our supplier, give it to an inspector to say, we want you to check dimension number 1 first. Give it to our CMM programmer to say, when you program this flatness, it has to have this number on it, so we can identify on the CMM report or the inspection report, have a correlation between the two. And regardless of whether it's manual or DCC type programming, the output of that is to obviously produce an inspection report that shows if the part or the process is good or bad, and link that back to the dimension numbers. So you can see these don't really align because I've got 9 over here and only 7 over here, but it's just an example. So again, we often have to produce those first article inspection reports, or FAIs, and either include them with our part, send them ahead of time so that somebody knows what we're shipping them was checked here, and there's traceability to that. And after all the approvals, it's obviously ready to ship. The challenge with that current method of ballooning drawings, writing CMM programs, producing the Excel sheets with the specific layouts, they're very time consuming. It's something that's been done a long time. People are transitioning away from this manual type approach, but SolidWorks Inspection is designed to automate this and contribute to the overall workflow right to the point of traceability. And again, SolidWorks Inspection is not related to the actual inspection of the part. You're still relying on tools, calipers, CMMs, gauges to do that. We're going to leverage the front end and the back end of that data flow to capture and share the information correctly. What's new in SolidWorks 2021? There's been a couple of small additions, and then we'll do a live presentation on what I think is the biggest value-added function. So in the SolidWorks Inspection add-in, you can read there's actually a new template folder structure, so that if you've got multiple users, multiple environments, multiple computers pulling off the same, that all your inspectors and people can be pulling from the same template file. That there's a little bit more value-added control to allow you to control those templates. Really nice new feature on the add-in side, and I'll show you a little bit on the add-in side in a few minutes. On the inspection standalone, or what I call the client side, there's been 2 really nice upgrades. One is these new VDA type target symbols. It's just a type of symbol that you can now, instead of just putting a circular dimension, you can now put a VDA style balloon. Another feature here is with the grid function. The grid is now customizable, so it's really nice. You can control the number of grids in both the vertical and horizontal plane, and go from there. What I would like to show you is what I think is my favorite new feature of SolidWorks Inspection, and one I think you'll get a lot of use out of, is, I'm just going to switch over to my client here. So here I am in SolidWorks Inspection 2021, and I'm going to start a new project. And I'm going to select just my default template. And what's new, in the past we would have typically picked off of PDF drawing files, or SolidWorks Inspection 2D files generated from the add-in function. What's new in this version, and you'll see at the very end, is the ability to open up a SolidWorks actual part file. So we're going to show you this really cool new function, and I'm going to pull it from my demo files and call it for the client, and I'm going to hit open. Yes, I know I'm in beta mode. And what you'll notice is that we get a 3D model view from our SolidWorks file. And right now it kind of looks pretty plain. But if you notice up here, we've got a new pull down. And when we click on it, we can actually say, we can double click on it to get it in the view that we want. And it'll also show all of the dimensions, all of the MBD that was actually associated with that view. And we can then just right click on it and say extract dimensions. A really nice new function there that actually goes through the database, goes through the SolidWorks file, reads the MBD functions, and creates the layout for us. You'll notice, and I'll come back to this later on in the presentation, it creates this kind of report file in a way that we can link to and do other things with once we've actually measured the part. So a very, very high, really cool new feature. If you've used MBD on your model to begin with, is to be able to leverage that information downstream, and rather than having to create 2D drawings and all of the associated thing, which SolidWorks inspection can do on its own, rather than having to go through those exercises, you can actually go straight from the SolidWorks with the MBD in it right into the client and save you a lot of time and money. And again, you can actually go and create all your standard reports, PDFs from here, and all your documentation that you need to otherwise. What I'm going to do is take a little bit of a step backwards, because we've kind of taken a big step forward, showing you this new function of how in the client side we can take advantage of MBD and SolidWorks inspection together. I'm actually going to loop back into my SolidWorks inspection folder, my SolidWorks main view, and I want to show you how that can also work in design mode. I'm actually just going to close this one, don't save, say file open, and open up the full part model this time. It's got a lot of MBD on it. We just cleared some of those things up for. And one of the neat things that you can do, again, there's the same MBD, a little part with lots of information on it, is I can actually use SolidWorks inspection. This is where we're using the add-in here to walk through our walk through our CAD model and assign balloon numbers based on the objects. So you may or may not have seen this before. SolidWorks inspection has been used a lot in the 2D drawing level, but you can see it's actually going through and labeling everything associated with an MBD function. So again, using an example of using SolidWorks MBD and SolidWorks inspection together. And the really nice thing of that, it's doing this in 3D space. It's doing it by saving each individual view. So again, if we went out into e-drawings, it would save all those views, and great for sharing information that way. And I'll just let it finish up here and spin it around. There we go. So you can see now that we have all of the balloons, and again, I won't do it, but you can see that you can export straight to an e-drawing from here. We can actually publish to a couple of other different formats for producing FAIs, because we haven't actually measured anything at this point. And that's kind of a great segue, because what we're going to do now that we've shown you a couple of the new features of SolidWorks, how this impacts downstream. So the next step is we need to go through the measuring process. I'm going to introduce David from our team, and David's going to show you how we would take a model like this with MBD on it and use it in the inspection process.
All right, thank you, Rob, for the introduction. So good afternoon, everyone. My name is David, and today in this portion of our presentation, I'll be taking you through how we can use 3D scanning technology in order to go from a physical part that we have and in a matter of minutes arrive at a full inspection report that lists the quality of our part through the use of inspection capabilities in GOM as well as SolidWorks. So to start off this presentation, let me first take you through an introduction of who GOM is as a company and talk about the type of technologies that they provide from the world of 3D scanning and inspection. So GOM is a leading optical metrology company that is currently operating in Braunschweig, located in Germany, and they offer contactless, accurate inspection capabilities through the use of optical 3D scanning technology. They provide rapid, high-resolution capture of data through the use of these 3D scanners that make use of specialized cameras as well as fringe projection technology in order to produce a detailed point cloud of the data. Once we have this 3D point cloud, we can polygonize it to turn into a smoothed out mesh, which we can then use in the GOM Inspect software to then calculate out our measurement results. So whether we want to check for common elements such as dimensional analysis, GD&T characteristics, we can also do full 3D surface comparisons as well as material thickness plots, create inspection sections to analyze it across a certain plane, and much more through the use of GOM technology. So now that we're a little bit more familiar with GOM as well as the type of solutions that they provide, let's take a look at an example of a system configuration that's used for 3D scanning. So here we have a picture of the setup that was used to scan this part, and we'll quickly go over the different components that make up this overall system. So first up, we have our ATOS Q 12 megapixel sensor, which is able to capture 12 million points of data with a single scan, and it's installed with a 500 millimeter measuring volume. So the measuring volume simply pertains to a boundary box of which the part that we want to scan must fit inside reasonably for us to be able to capture all the geometry of the part in an optimal way. So in order for us to be able to scan larger or smaller objects, we would need to adjust the measuring volume of the sensor accordingly. And this can be done either by changing out the sensor to one that has the appropriate measuring volume installed, or in the case of our ATOS Cube, we have a flexible system where we can uninstall the lenses and then install a new set of lenses that will either increase or decrease the measuring volume as we need. Our ATOS Q sensor is also mounted on a manual stand that we use to reposition the sensor itself. So whether we want to change the angle of attack or if we want to increase the height or depth of the sensor, we can do this with the help of our stand. And the reason for this is so that we can get our camera to be able to be placed in the optimal view to capture the remaining geometry that wasn't able to be picked up by previous positions. Next up, we have our automated rotation table that's synchronized with our sensor. And the reason we have this table is so that we can automatically have it rotate the part to get it to a new scan position. And then once it arrives at its new position, the sensor will automatically go ahead and take a scan of the part. So we can program this in the software to either run a set number of increments out of a full 360 rotation and repeat that as necessary or readjust the programming as necessary to capture the data in the most efficient manner. So this is all connected to our computer, which is running GOM Inspect Suite software. And the software is used for system operation as well as for inspection processes later on once we capture the data. So you'll notice as well on the table itself that there's a number of different markers that have been placed, and these are known as reference points. So reference points are used for the purpose of tracking, self-regulation, and to combine separate scan series. So these reference points are the system's way of determining where it has moved in relation to the original position of the part, so that no matter where we position it, whether we reposition the sensor with our stand, or if we rotate the part with our manual or automated table, the software is able to always have that recognition of its orientation relative to the part. And this way, whenever we take a new scan, it knows exactly where that new scan needs to be located because it has that knowledge from the reference points. So these reference points also allow us to have the self-regulation feature where the system is able to recognize when there is a decalibration that exists or if there is any movement that's affecting the part or the sensor, as well as if there's not enough reference points for it to be able to calculate out the transformation. So in addition to being used for tracking and self-regulation, the reference points are also used to combine separate scan series in the case where we need to reposition the part's orientation on the table to capture remaining geometry. So depending on the part, there will be instances where you'll be required to actually change the orientation of the parts on the table in order to capture any remaining geometry that wasn't able to be picked up in a previous orientation. And this is done by capturing the data in multiple separate scan series. And once we have all the data that we need, let's say we've placed a part in 3 different positions, then we would have 3 different scan series that are independent of one another. The way that we can combine it all to be aligned into a single mesh is through the use of these reference points that are then placed on the part itself in all 3 different positions. So because these common points will not be moving and they are on the same exact locations on the part in all 3 of those different positions, as long as we can capture those reference points in those different positions when we scan it, the software is able to compute the transformation matrix to combine each of them into a single uniform source. So all of these different components combine to give us an overall system configuration that we can use to successfully scan any part that we have. So now let's jump to a couple of videos that will showcase the part being scanned by our ATOS queue and setup shown here in real time. So now we see our ATOS queue being used to scan the part with our automated rotation table. And you can see that the queue is projecting a blue light fringe projection pattern across the surface. And based on how these patterns deform according to the surface geometry, the cameras on the left and right are able to calculate out 3D point clouds of the data to populate into the software. And now that we've switched over to the software view, you can see those reference points on the table and the part being recognized with a unique value. So as we move through the 10 different positions of this full rotation, the sensor will know exactly where it has moved to relative to the position of the part, and accordingly the software will put the new scan data into the correct positions as we see here. So we will basically continue to do this to capture any geometry that was not able to be picked up by previous scans, and we do this by either repositioning the sensor, repositioning the part, and then continuing to scan until we are satisfied with the results. So now let's take a quick look at how we can transform scan data to align them into a single source, and then polygonize the result to create a final smooth mesh profile. So here on the left, we see that for this part, we made 4 separate scans. So each scan was taken of the part after it was positioned in a new orientation on the table. So to combine these separate scan series, all we have to do is identify at least 3 common points that exist in 2 or more of the different scans that we took. So let's begin with just transforming this scan to data. So here we see that the reference points are marked as green dots on our software. And all we have to do in order to transform this data into a different scan, so let's say scan number 4, all that's needed is to click at least 3 common points on our part. And then we see through the use of those 3 common points, the software is able to match up the respective 3 points on scan 4 and combine the 2 to create a single source. So we would basically continue this process with all of the other scans until we have a single data set that combines all the different scans that we took to create this one uniform mesh like we see here. Now the last step, once we are satisfied with the data that's been captured, is to polygonize. So the polygonize process simply turns this point cloud data into an actual triangulated mesh, and we have a number of different post-processing options we can take. Typically, we just use the standard operation, so we'll go ahead with that. And in a matter of a minute or two, we will arrive at a final smooth mesh profile. So now that we've completed the polygonization progress, we can see that we have arrived at a final mesh profile of the part. And we can even take a look at the actual mesh structure just to look at the point density that we have with our high resolution ATOS Q sensor. So this allows us to very accurately capture all relevant data that we can use to then either measure the part or process it for the purpose of other operations such as 3D printing or reverse engineering in a software package for CAD. So up to this point, we've covered in detail how to leverage GOM's 3D scanning capabilities to create a digital copy of our part in the form of a 3D mesh. Now in this portion of the presentation, we're going to discuss how you can combine GOM's inspection capabilities with SolidWorks MBD and inspection to create a seamless transition from 3D design to 3D inspection. So once we have our 3D scan data of the part, we can use it in the GOM Inspect software for measurement analysis. So in GOM Inspect, we can create different inspection elements directly on the mesh model itself, whether we want to check for different dimensions, if we want to apply GD&T characteristics on certain features, or calculate things such as material thicknesses, surface comparisons, section outlines, and much more. Now, a great feature that we can leverage with GOM Inspect is actually the capability to combine it with SolidWorks MBD and Inspection for rapid quality analysis of our parts. So let's take a look at how exactly we can leverage all three of those different software packages to combine into one single solution. First, we start off with SolidWorks MBD, where we have our 3D CAD model of the part, and where we can apply our critical product manufacturing information directly on the model itself. So here we see an example of the CAD model with all the different PMI that's been applied onto it. And once we are satisfied with all the PMI we have, we can export it as a Step 242 file from MBD, where it will embed all this information into the intelligence step file that we can use in GOM Inspect Pro. So once we have this PMI enriched CAD file from MBD, we can load it into GOM Inspect Professional to have the software automatically create all of our inspection elements for us and calculate the results once we align it to the mesh data. And finally, once we have our inspection results in GOM Inspect, we can export these results in the form of a CSV file to be interpreted by SolidWorks Inspection Downstream, which we can then use to verify our design and then create our first article inspection reports. So now let's transition into a demonstration of how we can combine all three of those different software packages to create this cohesive solution. So now we have SolidWorks opened up with our MBD add-in enabled, and you can see that on our 3D CAD model, we've already applied all the different PMI on the defining features of this part. So we can see different elements such as dimensions, angles, GD&T characteristics, as well as datum references that the GD&T refers to in its check. So once we've completed the application of all these different inspection elements, we can then publish it from SolidWorks MBD directly as a Step 242 file, which again will embed all of the information created here into a single step file that will then be used in GOM Inspect Professional to automate the process of creating these different inspection elements. So now we've switched over to the GOM Inspect software, where we have our 3D scan model already loaded in the project. All that's left to do is simply bring in that PMI enriched step file that we created from MBD and import it into GOM Inspect and add it to this part. And as soon as I do this, you'll see that the CAD model appears on the graphics window and the software begins to create all the different inspection elements that was created from the MBD portion of the software. And we can see that each of these different elements have now been populated. And all that's left to do is simply align the mesh data to our CAD data in order to create the relationship between the two and then compute the inspection results we want to see. So now that we've aligned the CAD data to the mesh model, where you can see that the CAD is represented in blue and the mesh in gray, we can then also check the status of our results coming from the MBD that was applied in SolidWorks. So you can see on the left-hand panel that under inspection, we have all the different GD&T characteristics listed, as well as the dimensions that were applied from SolidWorks. So if I turn on the visibility of some of these different elements, I can start to see the results of the inspection. And you can see that we have a nominal value, which represents the ideal value that was calculated from the CAD model, and then the actual value. So the value of that check as it pertains to the mesh instead of the CAD. And there we can calculate a deviation from the nominal to the actual. And we have a quick visual representation of the tolerance check to see whether we are within or outside of tolerance. So this process allows us to very quickly go from the 3D design stage, where we've modeled our part in SolidWorks, use the MBD portion of the software to apply our inspection characteristics, and then leverage that model that has the PMI embedded inside to use it in GOM Inspect Professional and automate the process of creating each of these different inspection elements. Now, the final process in this step would be to export out all of these inspection results in the form of a CSV file that we can use in SolidWorks Inspection to load into a template and then calculate out all the results and have our first article inspection created for us as well. So now let's quickly summarize the 3D design to 3D inspection process that we just analyzed. So first, we have our 3D CAD model that's created in SolidWorks and the PMI that's directly embedded in the file with the help of SolidWorks MBD. With this PMI enriched CAD file, we can then scan the part to bring a digital copy of it into our GOM Inspect software and also import this step file with our PMI to have it automatically create all the inspection elements for us and calculate the results. The final step would just then be to export out all of our results in a CSV table, which we can then import into SolidWorks Inspection to create our first article inspection report. Now, to provide more detail on this last step, I'll pass things over to Rob to go over the process.
Great job, David. Thank you. And to start off on the last part of this presentation, we're going to loop back into the reporting side with SolidWorks and some additional options that way. So where we had previously discussed the part design, including MBD and all the new tools in SolidWorks Inspection, we've shown you how you can take that MBD file via step into a product like GOM Inspection that really produces three types of output. It's able to evaluate to the MBD for at machine analysis or in production analysis. It's able to export to an STL file or export the calculated results to a CSV. And that's a new enhancement that users should be aware of as well, that with this text-based formatting, one of the things we're able to do in the SolidWorks Inspection client is import those evaluations back into the system for first article inspection reporting. So you can see here in the inspection software, we have a new option called GOM import that is flavored to look for these types of evaluation and calculation files. And once it reads in that information, it's able to color code the deviations linked to the balloon labels. So you're able to get not just an inspection report off of the GOM system, but also use the SolidWorks system as a reporting engine. That way, once you've got it in there, you can use the additional tools in the SolidWorks Inspection client, such as exporting to an FAI Excel sheet and additional tools like that. Another tool that's new to CAD Micro Solutions is going to be shown here, where we follow the exact same flow of using MBD data and SolidWorks Inspection, but this time using a new product that lives inside of SolidWorks called Checkmate for SolidWorks. Now this is a third-party add-on living in the SolidWorks community, and what it's going to do is allow us to import scan data or import CMM data into SolidWorks for analysis. So if there were strict restrictions that we didn't want to do reporting and analysis inside of a product like GOM, we have a new value-added feature to do all of this analysis inside of SolidWorks. And we can also use that MBD infrastructure to actually write CMM programs. So not just import data, but actually use the framework for additional things like CMM programming. And from that imported data, we can also produce the same FAI reports that we populated in the other example. So at this time, I'm going to switch over to this new software and give you a 3 or 4 minute demo of what it's like to use.
So here we are in Checkmate for SolidWorks in 2021. It's the same file that we started off at the beginning of the presentation with embedded MBD and SolidWorks inspection balloons. And what Checkmate for SolidWorks is able to do is able to extract all of the information embedded in the model and convert it into what we call a nominal template. And it's gone through the drawing already, it's finished, and it's converted all of the CAD objects into metrology objects, such as planes, cylinders, circles, lines, things that would need to be interrogated and measured on a typical CMM device or a GOM inspection device. And you can see here's a browser or a listing of the feature. We call this the programming browser. And what you're able to do is see how the balloon numbers for the relevant features are all kept and carried across for future evaluations. So it happens very quickly. It's audited and does a one-for-one comparison. And at the end of that process, you've got a new template, not just the CAD, not just the MBD, but a metrology framework that allows you to communicate with many, many other devices. There I am circling feature number 9, and you can see that feature number 9 in the drawing is the flatness evaluation. What I'm doing here is just going to be hiding the annotations for a second, and you can see what it's done here. It's gone through and put kind of all these little pointers and dots on things where a typical CMM may hit the part to measure it. So if we just hide that for a second, one of the things we're going to do is take that information and show you how you can output that program into a text-based program, just like a G-code for a router out of CamWorks or a G-code for a machine tool. We can output these into a variety of different languages and flavors. There's me trying to write it to somewhere I shouldn't, and I'm just going to write it to my demo files directory. And at the end of this, you'll see on the screen you have a text-based, what's called a DMIS programming language that you could simply move to any coordinate measuring machine for evaluation. At the end of that evaluation, you get a report. You can then load that back in and do further analysis with it. Additionally, what you can do with this software package is load that STL file that was created by David, and this is the exact one that he created, and we can load that into SolidWorks and use the Checkmate for SolidWorks tools to do part comparisons, part reports, GD&T evaluations, analysis and stack up evaluations, and all those types of analysis functions that happen outside of the CMM room by typical process engineers. So here's just a view of some of the chromatic displays you can do as well. And what we would then do is analyze the map, because right now it's just best fit on the model based on its geometry type. And we would have it walk through the nominal template that it created and interrogate the point cloud and come up with all these evaluations that would be that shows you where it's done on the model and where the inspection types are. So some very powerful software that way, and we look forward to sharing it with you.
All right, so this brings a conclusion to our presentation. And what we've shown you this afternoon is some new things about MBD, SolidWorks inspection, program-free inspection with our GOM systems. No need to write programs, just place it on the table, capture high-quality data. A variety of different tools within GOM or Checkmate for SolidWorks for part and process analysis. A variety of different ways to produce first article inspection reports and PPAP reports. And stay tuned, in the future we're going to be linking all of this back into Delmia Works for Industry 4.0 and transparency considerations by all the end users. Thank you very much for paying attention. We appreciate your time.
All right, wonderful. Thank you very much, Rob and David. We do have some time for some questions as promised, and we have had quite a few in the queue throughout the presentation here, so I think we'll go ahead and get started, but feel free to keep them coming for us. Rob, I'm going to throw this first question your way. The question is, if you're not involved with quality, where is the MBD benefit?
That's a great question. In the context that we've shown it today, it's definitely been leaning towards the quality industry, but it's really been about the communication and how do we leverage the information that is embedded in the model for other applications. So in the example of using Checkmate as an example, it uses it for a variety of different purposes. CamWorks is the best example, is using it for tolerance-based machining. So the more information that we put in the models that way is not only passed through into products like those, or SolidWorks' own e-drawings format that you could use between customers and suppliers, for example. The more information we put in there, the more we're leaning more towards the Industry 4.0 compliance as well, of being able to share everything, capture everything, and that. It is definitely an evolving technology. It's leaps and bounds from where it was 4 or 5 years ago in its infancy, and products like GOM are using that information to quickly inspect things. But it's a great question, and the short answer right now, it is being used to simplify drawings, communicate things faster, and slowly finding their way into products like manufacturing packages, such as CamWorks.
Great, thank you, Rob. David, I think I'll direct this next one at you. The question is, I have a mechanical arm with a probe on it. What would be the big difference between it and scanning the part?
Right, so let's picture the probe. So a probe machine is simply a device that has a singular point, which it uses to tactile measurement strategy. So actually touching the part at various locations on the defining features in order to extract a geometric profile to then analyze it in a metrology sense. So the biggest difference between a mechanical probe and something like an optical metrology system from GOM would be, first of all, the amount of data density that we have in comparison. So when we talked about the ATOS Q sensor that we saw earlier this presentation, I mentioned that the 12 megapixel sensor is able to capture essentially up to 12 million points of data with a single scan. And if you compare that with singular data points that you're collecting one by one with a mechanical probe, already right there, there's a huge difference in the amount of data points that we're able to extract and use in order to create the measurements that we want to see. So that would be probably the largest difference. The second one would be as well in terms of programming. So when you have a mechanical arm, you obviously need to tell that arm where to probe on the part, and to do that, you also need to know in and out the defining features of the part, where exactly you want it to probe, and just so that there's no sort of interferences and that you're collecting the data that you need. However, that is all eliminated with our GOM scanners, because all we have to do is, no matter the part, we just place it on the table and just press the scan button on our computers, and then the scanner will go ahead and capture the geometry. And as long as it can see the features that we want to extract, it's able to create a point cloud out of that. So that adds up to the efficiency level of using a GOM scanner, with the sense of not being able to program it in any specific way to get all the data. You simply just have to place the part on the table, press scan, and in a matter of a couple minutes, you'll have that. So those two factors, I would say, are the two biggest differences between something like a GOM system, which uses optics, and another system that is more on a tactile measurement system.
Perfect, thank you, David. Another one here for you, David. Does GOM Inspect have the ability to read in SolidWorks Direct? Is that extra?
Right. So we saw in the presentation that in order to leverage the MBD data we had in SolidWorks, we needed to export it as a Step 242 file. So this is a specialized file format, which actually programs the CAD file to have the critical PMI in the extractable features of the part. As of now, you can import in native SolidWorks parts, as well as some other native CAD files from a few other CAD softwares. However, you need to have the GOM Inspect professional version of the software in order to leverage that data with the PMI. There is a GOM Inspect free version that's available for download for anybody who wants to get started and take a look at the world of metrology using GOM systems. All you need is a scan file you can get from any sort of scanner that you may have, or any mesh data STL that you had from before. And you can use the free version to simply inspect the part with the same way, aligning a CAD model to the mesh, creating your measurements, However, you just don't have that automated feature we highlighted here in the presentation with using the PMI export from SolidWorks MBD.
Great, thank you, David. Rob, I think this next one is best for you. So the question is, how big of an investment is it for companies to switch to MBD?
Great question. Difficult answer. From an infrastructure point of view, it's quite easy and quite inexpensive. From a philosophy, policy, and procedures and math point of view, and actually going through the exercise of an organization changing from full layout 2D drawings as the historical approach to full 3D, it is a big change. You can't hide from that. Your traditional methods of communicating the requirements way that may change internally or externally. It's a big change, and it's more philosophical than technical. And the technologies such as SolidWorks MBD are enabling that. Other products such as Elysium that allow you to move PMI information around a lot easier between CAD systems is obviously improving in that marketplace. So I think the technical end is getting there if it's not there now. But infrastructure-wise, it's a big change.
Great, thank you, Rob. David, another question for you here. How would I know if I should be doing the part evaluations at the machine or offline?
So I'm going to assume that at the machine just simply means within the GOM inspect software directly. So there really is no rule, like you don't have to specifically use one package or another to do your inspection. It's more so based on personal preference or the company's preference. So if you do, let's say, for example, you have a GOM scanner, which already does come with the GOM inspect license, you can go ahead and scan the part and directly within that same software, switch over to the inspection workspace and get started on measuring your parts. However, there may be cases where people designing in SolidWorks, for example, may be just more familiar with that sort of environment. So Rob also showcased the Checkmate for SolidWorks add-in that's available, where you can do all the part evaluations directly within the native SolidWorks interface. So if that's more up your alley, by all means, you can go ahead and do that. That's no issue, whichever software you choose to go with for the inspection side of things. The only thing that matters is as long as you have good quality data in terms of the digital copy of your part that you can evaluate to, as well as having the ability to analyze it against the CAD model definitely helps in terms of that as well. So the main answer would just be it doesn't really matter which software you use, it's based on your own personal preference.
Wonderful, thank you, David. We did have a couple questions here inquiring about getting the recording for today's session. So yes, for those of you who missed it, we certainly will be sending out the recording to you over the next couple of days here. And if you do have any further questions at that point for Rob or David, feel free to just respond to the email or reach out to your account manager, and we'd be happy to put you in touch with these guys to get you the answers that you're looking for. I think that's about it for us today. Once again, thank you very much to Rob and David for a great presentation today. Thank you to all of our attendees for joining us for this session in our Enabling Canadian Innovation Launch series. So thanks again, everybody, and take care.